Hello mathematicians. Our next graphing exercise is sketching functions by multiplication of ordinates. So that includes multiplication by a constant and multiplication of two functions together. So if a function is being multiplied by a constant, then the simplest thing to do is to plot the function, and we just multiply all the ordinates, the y values, by whatever the constant is. If we're going to graph a function which is a product of two other functions though, then we would follow the process we've done before, which is to initially draw our two separate graphs and then consider these individually and literally multiply ordinates at special points. So there are a couple of special points, and these are probably the two most common. So where either curve has an ordinate, a y value of 0, then obviously the product is 0. And where either curve has an ordinate of plus or minus 1, the product also is easy to find. So if we consider this curve down below, I'll just slide it up a little. If we consider these curves here, then we can see sine x, the blue curve just here, and cos x, the red curve, and we're going to try to look at what sine x times cos x looks like. So if we use these guidelines up above here, when either curve has an ordinate of 0, so if we concentrate on the sine curve to start with, then just here we've got an ordinate of 0, here, 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 and here. So at any of those points, their product must be 0. And likewise for the cos curve, we've got an ordinate of 0 there, and there, and there, and there. So again, at any of those points, the product, and there, any of those points, the product of the ordinates must be 0. And now if we look at when either curve has a plus or minus 1, so again for the sine curve, we've got a plus 1 there, which just happens to correspond to the 0. We've got a minus 1 here, which again corresponds to 0. It's just convenient that these are all corresponding to 0. So there's nothing exciting there. And for the cos curve, I think the same thing's going to happen. That 1 is corresponding to a 0. Yeah, so because of the nature of sine and cos, the 1s of one curve will line up with the 0s of another. It's a bit unfortunate, but essentially, if the two curves were a little bit different, then when we multiplied by 1, of course we don't change. Our new curve has the ordinate which is the same as on the curve that we're multiplying by 1. Now we then just do, I guess, some simple multiplication. So if we look at this point here, for example, it's some number. I don't know what the number is. We could figure it out. But both of the numbers, the one on the cos curve and the one on the sine curve, are less than 1. So when we multiply two numbers less than 1 together, we will get a total which is even smaller. So if we went through and just considered points, we'll end up doing a dot to dot, which is the green curve here. Now the sine curve and cos curve example was a bad one for me because it just like they all merge into each other. So let's have a look at the examples down below. So if we background it before we have a look at GeoGebra, then for our first one, we know that y equals x is going to run through there. So that's this part, that's being multiplied by e to the minus x, and we know e to the minus x runs down like this, and that will pass through 1. So if we look at the product of those, with particular regard to the points that we made above, then on this curve, the value of y equals x is 0, so when we multiply 0 times whatever e to the minus x is, we'll get 0, so we'll pass through there. That's probably the only point of much significance on here, because our 1 on this one happens to line up with a 0. I guess we could also come out to wherever 1 is on y equals x. Because I haven't drawn it all that accurately, this point here, when y equals x on this curve, that won't be all that easy to determine. It will happen when the value of x going out this way equals e to the minus x. But the main thing is that that product is going to involve two numbers which are less than 1 being multiplied together, so the product of those will be lower than that point. And when we actually got to a 1 out here, that 1 is being multiplied. I don't know why this is disappearing, but that 1 out there is being multiplied by this value, whatever it is. So 1 times that gives us that. That dot should be down here. Having real trouble getting the dots to stay on the page. I'm not sure why. So yeah, we've got this much of the curve. When I then think about what happens out here, I'm multiplying that x value by an increasingly diminishing e to the minus x. So that's going to give us a smaller and smaller value of the product out here. And on this side, I'm multiplying negative x by a rapidly increasing positive value of x there. So I'm going to be getting a big negative number, which is bigger than negative x. So my curve is going to go vaguely, and it's very vaguely, like this. And on this side out here, because I'm multiplying x by a decreasing number, it's going to drop down as well. Now that's a horrible attempt on my part, so we'll have a look at it on GeoGebra, see how we go. So here on GeoGebra, we can see our curve of y equals x. We can see what y equals e to the minus x looks like. So to get our product, as we said before, we can see that when that point is 0, then 0 times 1 means that we pass through that point. When at this point here we've got two numbers multiplied by two numbers which are less than 1 being multiplied, so their product should be even lower. At this point we've got this one multiplied by that value, so that product should be whatever the height of e to the minus x is, and then our curve is going to go on after that. So let's put that in. We can see our resultant curve just there, and I'll zoom in a little bit. So if we notice the behavior, it's as we said, that something less than 1 there, actually equal to e to the minus x there, not much multiplied by something a bit more, so it's up above the curve, and it drifts down gradually so that out here they both curves head off asymptotically towards 0 as x tends to plus infinity. And down the bottom we can see that we're heading off down here, very similar fashion to the exponential, because this one starts to dominate over this one. Okay, this should be some more interesting drawing on my part. Y equals x, sine x, which is going to go something like this. I won't get too carried away with too many cycles. Why is that disappearing? I don't know. We know the height here is 1 and minus 1. So they all pass through, or I'm attempting to show that they all pass through 0 there, so their product is 0. Just here, the product will be 0, here and here, all of those points the product will be 0. This point here, where we've got a number which is less than 1 on the sine curve and one which is less than 1 on the y equals x curve, so their product will be less than 1. Likewise here, product less than 1. Again, they're disappearing. And in between, so when this is 1, that'll be 1 times the height of this curve, so that'll be just on the curve. And here, and in between here, again, we've got numbers which are going to multiply. They'll all be less than 1. I'm not even going to try to do a sensible dot to dot there, so we'll go straight to GeoGebra. So here we have our two curves. Again, think about where either curve is 0 and then where either curve is 1. And look at what we get. Really interesting curve. So our 0 points, anywhere on the sine curve, our product is 0. Concentrating on this little bit in here, when our sine curve is 1, it's 1 times whatever the y value is. You can see my scale was so far off on my little sketch that it wasn't even useful. So 1 times, so 1 on the y curve, sorry, 1 on the sine curve multiplied by the ordinate on y equals x means it passes through y equals x. And likewise up here, I'll zoom out in a moment, we've got negative values here, so -1 times whatever the y value is, which is way up here, is going to give us the value on the y equals x curve, but as a negative. Now I'll just zoom out, because this curve is really interesting when you zoom out. I'll go a little bit further even. Try and move this down. Okay, really interesting curve. It's sort of like we have a y equals x and a y equals minus x, and the sine curve trapped between them, just launching out. So yeah, really fascinating curve. You can see why I struggled drawing it. Now my curve sketching can't get any worse. So once again, y equals x, missed the origin, but we know we've got 1, 1 out here somewhere, just to give us a vague idea of scale. And for my log curve, we know it comes up like this, and it passes through, sorry my pen's not, passes through 0 just here, so the product of the two is 0 there. Product of the two is 0 here, but because the log curve doesn't exist at x equals 0, the domain of our product is only going to be where x is greater than 0. Now out this side, we can see that we're multiplying the value of y on here, the y equals x curve, by a number which is smaller than that. So the product will be bigger than this curve, but over time this curve will tend to dominate the y equals x curve. In here we've got a little bit of a worry, because this curve is heading down towards 0, this curve is heading off towards negative infinity, so our product is a number which is heading towards 0 being multiplied by a number which is heading obviously away from 0. Which one of those dominates? So do we end up going down this way with the infinity dominating, or do we head towards this point because of the 0? What we really have to do is to, well, I guess we could plot a few more points in here, but we might have to go for calculus as well. So if we think about our original function and we differentiate it, it's a product, so we put down the first multiplied by the differential of the second, plus the second, multiply by the differential of the first, which is just 1. So we get y dashed is 1 plus log x. So is there a turning point? So there would be a turning point if log x equaled minus 1. So if we took the exponential of both sides, that would give us x equals e to the minus 1, or 1 on e, which is, about a third. So somewhere down here there is a turning point. So our curve is going to have this sort of shape in between. And as we go on from there, we just get the product of these two. That's going to go up very vaguely like that. If we look at our two curves here, our log x and our y equals x, and I'll just type in their product, and we can see the product here roughly as we predicted. I might zoom in so we can get a closer look at that turning point. So that turning point just around here, as we said, around about a third, 0.33, and after that we've just got the product. So before you launch off onto set 3, what are the things that you can take out of this? Well, I think the first is that draw a nice big sketch, so try to do a squidgy little one like this. Have a vague sense of scale, clearly, because when you don't have anything like a reasonable sense of scale, you run into difficulties. Look for points where either curve or both curves are equal to 0 or plus or minus 1. Look for where you've got a product of terms which are both less than 1, and do a fair bit of thinking. And if you're unsure, or possibly even as a matter of course, find the first differential to see whether there are turning points, and if there are, where are they? And if need be, what their nature is. And we didn't need to check the nature of this one here because it was obviously not a maximum.